This is the second part of this video on a linear model example. So what we've done so far is we've, if you saw the previous video, we went through the steps of verifying that a linear model is appropriate. We did the first check of the scatter plot, and then we created the model, and then we used the model to create the residuals, and we saw that there's no pattern. So now we can move forward and describe the model and then apply it to make predictions. So I broke out the questions into two parts. If you're watching this and you just recently took a quiz on this problem, I changed it a little bit because I broke out the question, what does the correlation coefficient R indicate? That's slightly different than if somebody asks you to describe the model. So R tells us how strong the model is. R can be between 1 and -1. So it tells us the direction and strength of the model. The closer R is to 1, the stronger the model. Okay, so if we go up and we look at R, I believe it was 0.91. So it's positive and very close to 1. So the same way we wrote, basically you just rewrite what you wrote up here. We said the scatter plot shows, I should have said shows a moderately strong positive linear association between age and height of female infants. So we kind of rewrite that, only here we say according to R, there is a, and I don't think we need to say moderate. I think because we now see, it's more definitive, it's 0.9, there is a strong positive linear, and then instead of saying correlation, now that we've done the check, instead of saying association, now that we've done the checks, we can say correlation. So the strong positive linear correlation between the age of female infants and their height. Okay, so that's how we would interpret R. So you may be asked that anywhere throughout the problem. Now, let's move on. When they ask you to describe the model, there's really three things you should talk about. First, talk about the slope. Talk about R squared. These are probably the two most important. And then sometimes the X or Y intercepts. I said Y or X. Y is usually more appropriate, but the Y, let's call it Y or X intercepts. You should talk about all three in order to describe the model completely. So when it comes to the slope, I'll just say slope like this. What we can do is let's go up to the model, just go up to the model and find the slope, here it is, and put a 1 underneath it. So think about what that means. So if we had a line through here, if the change is 1, if we go over 1, how much do we go up? Well, we go up, so we go over 1 month, we go up what, 0.667 inches. So we say for every 1 month of age, the height of female infants increases by 0.6677 inches. And then say on average, right? Because we know that there's some variability, right? There's some variability. So the y hat is really sort of the average. We know it could vary about that line. So that's why we throw that in. Okay, so now let's talk about r squared. Well, r squared, if we go back and look, we want to convert that to a percent. So here it's 0.833 multiplied by 100, so 83.3%. So what that means is 83.3% of the variability in height is explained by the variability in months. So I'm just going to write that. So you just kind of sort of memorize it and say it often enough, and it starts to make sense. So we'll say 83.3% of the variability in the height of female infants is accounted for by their age in months. Okay? So what that means is, let's see, 1 minus 83.3, so that's going to be, let's see, what, 11.9, something like that. So there's some amount that's unexplained. So that might be due to other things, okay, like genetics or diet, who knows what. But so still, that kind of tells us the model is useful. Okay, so it explains most of it. Okay, now in this particular case, the y-intercept has meaning, because that would be, if we think about it, if we went to 0, that would be a newborn baby. Okay, so a newborn baby, when age is 0, this term goes away, and we get 19.39 inches. So we would say something to the effect that the model indicates newborn babies or infants. I guess that's redundant. Newborn, yeah, that is redundant. Newborn females. No laughing at the teacher. Okay, the model indicates newborn females are 19.39 inches in height. And then, of course, we have to say on average. Okay, so these are the three things that you need. Whenever you hear describe, talk about these. And then you might want to talk about the x-intercept if you have a negative relationship. And every once in a while, the x-intercept has meaning. And so to find the x-intercept, remember that if this is y hat equals a plus bx, all you have to do is say let y hat equals 0. So you plug 0 in here and use a little algebra. Let's see, what would that happen? What you would get is minus a over b is equal to x. So that would give you the x-intercept. So sometimes that's important. Alright, let's move on. So now we've bragged about our model. We've talked about it in many ways. So now we can use the model. If a child is 5 months old, how old do we expect? So our model is the expected value. So what we would do is we would just show your work. I know that maybe to some of you this seems really trivial, but on the AP test you have to do this. So 19.39 plus 0.6677 times 5. Just show your work, type it in, show this, and then tell us, interpret what this means. Do that automatically. You shouldn't have to be told. So according to the linear model, we expect a 5-month I don't know if that's very good wording. A 5-month-old female infant to be 22.69 inches tall on average. Okay? Alright, so we always like to do this to sort of see if you understand things. So what we're told, we're sort of given a point. We have a particular infant that's 5 months old, and they are actually 23.9 inches tall. So remember earlier that the residual is equal to the observed minus the expected. So here, or notation wise, it's equal to y minus y hat. So here we would have the observed value is right here, 23.9, minus the predicted value is up here from the equation, 22.69. And when you do that, I get something like this. Okay? So 1.29 inches. Okay, so interpret what this means. So it appears that the model, let's see, so this is bigger, the observed value was bigger than the model, so it appears that the model under predicted. The height of this female infant. Okay? That's all you need to say. We're looking for your understanding of over-prediction, under-prediction. Okay, so now finally, would you be willing to predict the height of a 10-year-old child with this model? So I give it away here by why not. So let's think about this just for a minute. We had 1-month-olds and 9-month-old babies, okay? And I'm going to make my scale really small. We'll see in a minute why. So this would be 26 and this is 19. Something like that was our range. So we had data something like this, okay, in this area. Not that much data, but just bear with me. Okay, so a 10-year-old, how many months is that? Well, there's 12 months, right? 12 months in a year, so a 10-year-old would be 120 months. So that's like, whoa, way out here, right? I don't even think that's to scale. So if we put a model through here, we're way out here. Okay, so the problem is we have no data to confirm. We have no data points out here to confirm that the model is relevant way out here. Okay, we do have data points pretty close to 0, so we're pretty confident that the y-intercept probably has meaning in this particular case. So this is called extrapolation. So would you be willing to predict the height? No. This would be extrapolation. There is no data to support the model at 10 years. Okay, something to that effect. Now, some people on the test, they talked about how, well, you know, there's growth spurts and you grow fast and then you slow down and stuff like that. Okay, that's probably true. That's probably true. But what we're getting at is in AP statistics, what we're getting at is we should only use the model to predict in the range where we have data. We don't want to predict out here. Okay? All right, so I hope that helps. That kind of goes through. These are the basic questions. Look for other videos to cover sort of some of the other things that we might do with this model. But these are sort of the basic questions that you need to be prepared for when you take the test. Okay? Good luck.